Hello, welcome to Math 253 Calculus 3 Cañada College. My name is Lapuz, the instructor for the course. In this video, we will take a look at another big theorem for this section or for this chapter. It's called Green's theorem. So Green's theorem is a way to relate two types of integrals. And the bottom line for our fundamental theorem of calculus and the fundamental theorem of line integrals is that we're saying we're taking the integral of a derivative and then we're going to evaluate it at the endpoints. And so let's see if those words or that particular phrase would follow along with this other fundamental theorem that we're going to study. So here's Green's theorem. Green's theorem tells us that we have a line integral of a vector field over a curve C, and that is going to relate with a double integral of the partial of q with respect to x minus the partial of p with respect to y over some region D. So if we kind of read this backwards and go from the right side to the left, we're saying a double integral of some sort of derivative over a two-dimensional region, and we're going to replace that with a single integral of the original function over the boundary of the domain D. And so that is going to be the way we can relate this to the other fundamental theorems that we studied. We can also take a look at this as some sort of circulation going around a curve C, and the orientation is going to be important for us, going in a counterclockwise direction. And as we go along this, we're going to follow the tangent vectors, and that's the computation for the line integral, if you remember, is computing the dot product between the vector field and the tangent vectors as you go along a particular curve. Now in this closed curve, you're actually capturing a domain, a region, and so what we're saying here is that if you take the double integral of some sort of derivative of a vector field over that domain, it's the same thing as calculating this circulation around the particular curve. Most of the time we're going to use Green's theorem when we're faced with a line integral and find that the line integral is kind of difficult to compute. And so if the line integral has a closed curve, then we can replace that with a double integral, which in our case is probably going to be easier to compute than the line integral. It's rarely, Green's theorem is rarely used going from a double integral to a line integral, but it is used sometimes, and one of the popular applications is to find the area. If we remember the area function, or the area, one way to find the area is to use a double integral and to put 1 as your integrand. Now, if we can imagine 1 as that relationship of the double integral where we have the partial of q with respect to x minus the partial of p with respect to y, and somehow extract a vector field from that, p comma q, then the vector field can be either 0, 1 or negative 1, 0, or actually it should be 0x or negative y comma 0, or it could be negative 1/2 y comma 1/2 x. In any case, those vector fields can be used in the line integral, and sometimes that might be easier to compute. An example of trying to find an area would be an epicycloid, and finding the area within the epicycloid could be kind of difficult because it's hard to think about what types of functions we can describe there. And so if we know the parameterization of the epicycloid, then we can use the parameterization as the curve, the closed curve C, and then we can evaluate that line integral. So in most cases, we'll see Green's theorem written from computing a line integral and computing a double integral. That would be easier. But in these weird cases where we have to find the area, we sometimes have to go backwards. Okay, and so that's the circulation portion of Green's theorem. Now we can also see Green's theorem. This is not usually called Green's theorem. This is usually called something else, but the idea of the flux going outward. This is sometimes called the divergence theorem on the plane, but the book calls it the Green's theorem in flux form. And the idea here, if you remember the idea of a flux in a line integral is what's happening, the vector field compared to the normal vectors. And so in this case, we're doing a line integral dotted with a normal vector, and so this is going to be your flux portion of things. And then we can replace that again with a double integral, but this time instead of the partial of q with respect to x minus the partial of p with respect to y, it's going to be the partial of p with respect to x plus the partial of q with respect to y. And we'll try to see what the relationship is between this derivative versus the other derivative that we've seen. And again, we'll see that this is sometimes called the divergence or the div portion or the div version of Green's theorem. Okay, so that is our overview of this section. Good luck.